Let's do part A. So here we have this differential equation, that is y prime plus 2y equals 2.8, and the solution expression is given as y equals c e power negative 2x, and we're also given this initial condition y of 0 equals 1. So basically we have to check if this solution expression satisfies this differential equation. So let's do that. Looking at the differential equation, we have this y prime, that is the derivative of y. So first, let's determine the derivative of y. So I write down y prime is the derivative of y, and this equals c is a constant. We should find the derivative of e raised to the power of negative 2x. So derivative of an exponential expression is e raised to the power of x. That is, here we have e raised to the power of negative 2x, and then we have to apply the chain rule to find the derivative of negative 2x. The derivative of negative 2x is negative 2. So I multiply this with negative 2. So therefore this simplifies to, I can put this, or I multiply this negative 2 with the c. So therefore I have negative 2c e raised to the power of negative 2x. So this is the expression for y prime. We will utilize this to substitute into this differential equation. So replace y prime by negative 2c e power negative 2x. So therefore we get negative 2c e raised to the power of negative 2x, plus we have 2y. So I put 2 and then multiply with y. That is, I should utilize the same y over here, which is c e power negative 2x. And this equals, we have on the right side 2.8. So let's check if this satisfies this equation. This is negative 2c e raised to the power of 2x, and here we can multiply this 2 with the c. We get 2c e raised to the power of negative 2x. On the right side we have 2.8. So we see that this negative 2cx gets cancelled with this positive 2cx, and we get 0 on the left side, and this equals 2.8. So this is not true. 0 is not equal to 2.8, and this means the given solution expression does not satisfy the given differential equation. So therefore we see that the expression y equals ce raised to the power of negative 2x is not a solution of the differential equation. We now determine the value of c by substituting the initial condition. That is, this is the initial condition. When x equals 0, y equal to 1. I'm going to plug in into this expression y equals c e power negative 2x. So therefore we get y equal to 1. So replace y by 1, and c e raised to the power of negative 2 times of x is replaced as 0, and this is basically e power 0, which equals 1. So we get 1 equals c times of 1, and so this gives us the value of c equals 1. So we have determined the value of c, which is equivalent to 1. Let's do part B. So here we have this second expression y equals cx cube, and we should check if this satisfies the differential equation. Since this has a y prime, I'm going to find the derivative of y, which is y prime, and this equals, we have c, which is a constant. The derivative of x cube is 3x squared. So basically y prime equals 3cx squared. We can plug in into the differential equation. That is, we have x times of y prime, which is 3cx squared, and this equals, on the right side we have 3 times of y, which is replace y cx cube. So here we have 3c is a constant, so I put that in front, and x times x squared is x cube, and this equals 3 is a constant and c is a constant, so we can write them as 3c and x cube, and this is true. Both sides we have 3c x cube equals 3c x cube. So we say that this expression, that is y equals c x cube, is a solution to the given differential equation. Now let's determine the value of c by plugging the initial condition into this solution expression. So we have to plug in x equal to -4 and y equals 16. So therefore this becomes replace x by 16, I'm sorry, y by 16. This equals c times of x is -4. So it is -420 cube. So here we have 16, and this equals c times of -4 quantity cube is -16. So this gives c equals -1 when we divide both sides by -16. So we determine the value of c equals -1. Let's do part C. Here we have the second expression, y squared minus 2x squared equal to c, and this is the differential equation, that is y prime equals 2x. So this differential equation is y prime. So basically we have to find the derivative of this expression. Since this looks like an implicit equation, we have to do the implicit differentiation. So let's do that. I'm going to find the implicit differentiation on both sides. So the derivative of y squared is, first we apply the power rule to find the derivative of y squared, which is 2y. And using the chain rule, we put y prime, which is the derivative of y, minus we have 2 times of derivative of x squared is 2x using the power rule, and this equals the derivative of c, which is a constant, is 0. So we can now divide all the terms by 2. So this 2 gets cancelled and this 2 also gets cancelled, and so this reduces to y prime minus 2x equals 0. I can now solve for y prime. So this equals 2x. I have the expression for y prime, which I can substitute over here. That is, replace y prime by 2x. We get 2x equals, on the right side we have 2x. So therefore clearly this is true. And this means the given expression, that is y squared minus 2x squared equal to c, is a solution. This is a solution to the given differential equation. Now let's substitute the initial condition to determine the value of c. That is, when x equals 1, y equals root 3. So let's substitute these values of x and y into the solution equation. Replace y by root 3. So therefore this becomes root 3 quantity squared minus 2 times of x is 1. It becomes 2 1 squared equals c. Root 3 quantity square is 3 minus 2 times of 1 square is 1, and this is equal to c. This is 3 minus 2 equals c. So it gives c equals 1. So we determine the value of c equal to 1 for this question. Let's do part D. So here we have this solution expression. Let me find its derivative, that is y prime, and this equals c times of derivative of secant x is secant x multiplied with tan x. So I'm going to replace y prime as this expression. Therefore, this equation becomes y prime is c times of secant x tangent x, and this equals we have y replaced by c times of secant x and then multiplied with tan x. So on both sides we have this expression, c times secant x tan x equals c times secant x tan x, and this is true. So we say that the given solution expression y equal to secant x is a solution to the given differential equation. Let's determine the value of c. by plugging this initial condition into this solution equation. So we have at x equal to 0, y equals pi by 2. Plugging it into this equation, we get replace y by pi by 2, and this equals c times of secant of x is replaced as 0, and this gives pi by 2 equals c times of secant 0 is 1. So we say that value of c equals pi by 2.